Welcome back. We are going to finish finally this dynamic array. I know I keep saying that, but this is the final thing we need to do, and that is implementing a cleanup function. So we're going to use free, which will free up the memory. So the actual function is pretty simple. It doesn't return anything, so it's a void, and we'll call it a cleanup. And of course, it takes in a type of dynamic array with a pointer to our array, and it is a function. So we will call free on the part of the array that actually has memory allocated in the heap. So that is, of course, the data. Now, I had a question, which was, when we malloc and when we realloc, we actually give it a size, which tells C how much memory to allocate in the heap. But when we free it, we are just giving it the pointer. We don't give it a size. So how does free know how much memory to free up? And it turns out that when malloc returned the pointer, it actually reserved metadata in a header slot directly next to, immediately before the address that it returns. So every time you malloc or realloc, it's actually reserving a sliver of space before the pointer it's given you, which has metadata that contains like how much memory this pointer is going to represent. So that when we call free, it actually looks at this address, looks to its left for the metadata, which contains the size data, and then it frees it up. So just some under the hood stuff there that basically answers why we don't need to give it how much memory to free. It also means that you have to only call free at the pointer at the start of this data. We could give a pointer to a slot of memory that is within the data array, but because free will look to the immediate left for the metadata, that will actually fail and it will cause chaos. So you can always only give it the start of, like the pointer at the start of the memory heap of that variable, if that makes sense. So some general cleanup rules. We need to set the pointer to null. So free, this pointer will be freed up, but we want to set it to null specifically, and that's just good practice in C apparently. So array data, and set it to null, and that way the program will know that that is a pointer that cannot be used. We're also going to set the struct values to 0, so we have a length, and we want to have this reflect the truth. The array has been wiped out, the memory's been freed, so the length is 0, and the capacity is 0 as well. Of course, we don't need to free these ones because these are properties that belong on the struct, which is in our stack, not in our heap. Cool. So that's the actual function there. What we'll do is we will use a leaks analyzer, basically. There's different ones for each operating system, so we'll use the one on Mac. What it will do is we'll run the function and it will look for any memory leaks. It's not completely looking for every memory leaks. It's looking for memory that has been allocated, that hasn't been freed, and that can't be reached. So hopefully I'll explain it in a little bit here. If I just call our cleanup function here at the end of our function and give it the address of the array, if I ran, let's just do it. So let's just compile it, wall wextra. We're going to give it this -g flag, which is the debugger flag, and then define the output as din array leak testing. And then we're going to give it the file, which is dynamic array.c. And then we're going to run this leaks debugger basically. So in Mac it's leaks. I think it's giving it a flag at exit, which means that it will run it through and then find the leaks at the exit of the program, which is when main returns 0. And then I believe it's this, and then it's the program name. So /din array leak testing. I may have gotten something wrong here, so we'll see. Nope. So it actually, we have gotten a free, there's no leaks, 0 leaks, so it ran correctly. So what if I didn't have this cleanup function? You would expect that if I compile it again and run leaks again, what would we expect? We'd expect that we didn't run the cleanup and so there would be leaks, right? But we'll see that that's actually not the case. It actually still reports 0 leaks, even though we didn't run the cleanup. And that's because this leaks debugger that we have on macOS at least, I'm not sure how it works on other operating systems, but because our array data has been allocated and there is something that's looking at, that is reaching that memory, then it counts it as not a leak because it's reachable. And it's when we are calling this result and this result here. When we run the get, there's something, we're still pointing at the array, and so it's still reachable, and therefore leaks finds that there are no memory leaks. So what happens if we comment out this stuff? If we never, if we don't have anything left to go and look for the memory that we haven't freed up. Let's compile again. Let's run it again. And we will see it has found a lot of issues. It's found an instance of a root leak. And the realloc in push, basically, so let's see, in our push function, this thing that was finally realloced, that was the last operation that assigned memory, is not reachable and it hasn't been cleaned up. And so there's an instance of root leak there. And I don't know what all this is. It might be a stack trace, I'm not sure. Let me know if you know. But that sort of is the end of that. If we run the cleanup and we don't have anything referring to the memory that we've cleaned up, this is the final proof that the leak is taken care of. Let's compile again. We'll run the leaks and 0 leaks. So the cleanup actually worked. Without this, if we didn't run cleanup, we saw that there was a leak. Now this cleanup makes our function clean, makes our program clean. So that's the end of dynamic arrays, thankfully. It took a long time, but I think we learned a lot about how C works and how it's sort of different from languages that I'm used to. And I look forward to the next section, which I believe is linked lists. So something a bit more complex, a bit more interesting. Please like and subscribe.